So today I like to cover some things on powers and polynomials. This will be like 11.1 through 11.3. And I may break this up into a couple of videos here as we move through here, so we don't have to have one big bulk video. Excuse me. So in this section, we're going to deal with what's called law of exponents. And we should be familiar with what an exponent is. And what we're going to start with is to multiply powers that have like bases. So the first thing we have to do is verify that the bases are the same. We want to use this base as the base of our product. And then what we'll discover is there's going to be a shortcut, add the exponents for the exponent of the product. So this rule is kind of times, instead of writing long words, a lot of times you'll see this rule written in kind of more of a symbolic form, a to the m times a to the n, where we keep the base the same. So a is called the base, and we actually add those exponents m and n. And that allows us to do the problem. So if I look at this first example, we want to find the products. Again, products kind of means to multiply. So if I look at this as multiplication, we have y to the fourth really means y times y times y times y times then y to the third means y times y times y. But notice how we have 1, 2, 3, 4, 5, 6, 7 y's connected by multiplication. That's where exponents come into play. And we can write that as y to the seventh. So that's kind of what we're doing mentally. But if I want to use a shortcut of picking up on the laws of exponents, notice how if we have y to the fourth times y to the third, notice how our base is the same. So we're allowed to keep the same base and add the exponents 4 plus 3, and that will give us then y to the seventh power. So notice how on part B, the bases are the same. So if you note, a really means a to the power of 1. So what I'm really got is I got 1a times 2 more a's. In other words, a to the 1 plus 2. That's going to give me then a to the power of 3. So if I want to multiply b times b, remember, there's just two b's present, so it's b squared. Or you have 1b and 1b, so you can say it's b to the 1 plus 1, which is b squared. That would be a simpler way of writing it. That's called multiplying with the same basis. So if I have x to the power of 1 here, x to the power of 3 times x to the power of 2. Again, since we're multiplying and we have the same bases, we can add those exponents together to get the answer. And we would end up with 6, so x to the sixth power. Notice here, x squared times y to the third, the bases are not the same. So we cannot apply the law of exponents here. So this is simplified. So simplified means really we can't go any further. So 5x squared, or I'm sorry, 5x cubed times 2x to the fourth. Notice how these coefficients, this 5 is multiplied to the x cubed, and this coefficient 2 is multiplied to the x to the fourth. So since coefficients are also connected by multiplication, we know we can multiply this then as 5 times 2 times then x to the third times x to the fourth. Because remember, if every little thing is connected by multiplication, we can rearrange things to put things that can actually be multiplied together. So 5 times 2 is going to give me a 10. But watch out though, x to the third times x to the fourth, we actually have to be adding those exponents, and that would be 10x to the seventh as an answer. So dividing powers with like bases. So division is like reducing fractions. So reducing fractions is a big thing we have. So remember, in reducing fractions, if the numerator and denominator are a common factor, that common factor turns into a 1. So we can use this concept in dividing out like powers. So what we're saying is, like, if I gave you 5 over 5, notice how the numerator and denominator are the same. Those factors are what we say cancel out, but they really divide out and turn into a 1. Because remember, if you check it, 1 times 5 gets you back to 5. So when you cancel out like factors in division, remember, that's turning into the number 1. So if I have x to the fifth divided by x to the squared, again, by definition, x to the fifth means x times x times x times, so there's 5x's there, lost track. and x squared means x times x. And notice how for each x in the numerator, we can cancel with the denominator. So we have two pairs of x's we can cancel out or remove, if you will. So what I'm left with is x to the third over 1. But since there's a 1 on the denominator, it's not required, because remember, division by 1 doesn't change anything. So we can just keep that as then x to the third. Notice how if we have a squared divided by a, that's the same thing as a times a over a. Notice how, again, we can just cancel out the a's. And that just gives us then a over 1 again, or we would just call that a. Now, notice the b to the 7th divided by c to the 5th, since those aren't the same bases, we can't do anything with that. That is considered simplified. If I look at d, I have m to the third, which again means m times m times m. If I want to divide by m times m times m, notice that these numerators and denominators will divide out, or we sometimes call cancel out. So everything is canceled out. But remember, this really just means 1 over 1, which is the same thing as simply 1. So if I have y to the third divided by y to the fourth, that's the same thing as y times y times y divided by y times y times y times y. So again, in fractions, we can divide out like factors. So remember, when we divide, that numerator does not turn into 0. That numerator turns into 1, and there's a y left over on the bottom. So we'd have those would be our answers, just using some of our common sense, using the concepts of reducing fractions. But what we also pick up on is we can be using subtraction as a way to do these problems. So another way to do this on these examples is actually apply a law. Let me see if I found that anywhere. Here it is. So if we have a to the m divided by a to the n, notice how I actually can subtract those exponents in this example up here. So if I look at the first one, notice how I have x to the 5th divided by x squared. You could have also wrote this as x to the 5 minus 2. So remember, you got to go numerator exponent minus denominator exponent, and that gives me x cubed. Here on part B, notice how you have an a to the second over a to the first. Notice how you could just subtract those exponents, 2 minus 1. So that's going to be a to the power of 1. But remember, if the exponent is 1, we do not have to write it. It's understood to be there. So a to the 1 just means 1a, or just simply write an a. Now we can't apply that rule here because the bases are different. But on part D, notice how we have m cubed divided by m cubed. So we could write this as m to the third minus 3. And 3 minus 3 is going to be 0. That's kind of strange, m to the 0. What is that? Well, remember, the answer we got was 1. So that means these must be equivalent. M to the 0 must equal 1. So we're kind of picking up on some special exponents here. 0 becomes an exponent that we need to look forward to as we move further into the problems. Here, notice how we would have y to the 3 minus 4. And notice how we get another strange exponent. 3 minus 4 is going to be y to the negative 1. And notice when we did the problem, we got 1 over y. So those must also mean the same thing. So some things we're starting to introduce is what's called a 0 exponent, and also what's called a negative exponent. So we're going to start to explore what they mean in our math vocabulary, our math understanding. So notice how we're saying here, any non-zero base raised to 0 power is going to equal 1 is what we're picking up on. And notice how we had this y to the negative 1. What we're picking up on here, an expression with a negative exponent is going to equal the reciprocal of the expression written with a positive exponent having the same value. So that's what they're kind of saying here as some rules. Anything to the 0 power is going to be 1. Of course, our base can't be 0, though. There's not going to be any meaning behind that. Another one that's kind of interesting here is this example right here, 1 over n to the negative 1. Notice how if we have a negative x1 at the bottom, and also if I take the reciprocal of that, it no longer is a fraction. It just becomes n. So that's a kind of a neat one there, is that one that we'll see more of. Also, if you multiply something by its reciprocal, we know that n times its reciprocal is 1. Notice how n times n to the negative 1, those basically mean they're reciprocals of each other. And notice how that gives me n to the 0, and that also equals 1. So there's some very close meaning behind that as we explore some cool things with some powers and exponents. So if I look at these examples here, again, you may want to pause the video and kind of practice them yourself and then come back and see if you came up with the same thing I did. So if I have x to the fifth over x to the third, notice how we want to write these quotients. So again, this is talking about division, but they want the answers using positive exponents. So by following the rule, this would be x to the 5 minus 8. But notice how 5 minus 8 is actually a negative 3. So this means to take the reciprocal of it, that's going to be 1 over x to the third. So notice how here we'd have a to the power of 1. So this really means a to the power of 1 minus 4. Well, 1 minus 4 would be negative 3. A to the negative 3 would be 1 over a cubed. If I look at this next example, y to the negative third divided by y squared. So notice how we could subtract exponents. Y to the negative 3 minus 2. But notice how we've got a bunch of stuff going here. We could kind of use the circle method. So that's how we have a negative 3 and a negative 2. So instead of thinking this is subtraction, remember subtraction is the same thing as adding the opposite. A lot of times I'll use circles to kind of help me organize that in my brain. So negative 3 and a negative 2, that gives me a negative 5. So it's y to the negative 5, which is going to be 1 over y to the fifth. Now, another way to do this problem, this y to the negative third over y squared, another way of doing it is make the negative exponent go away at the very beginning. So notice how I can move this negative 3 down to the bottom and it becomes a positive exponent. So we can't leave the numerator blank, so a placeholder of 1 becomes there. We have y squared times in this y to the third. So notice how this gets me to the same spot of this 1 over y to the fifth power. So look at this next example. Notice how, again, the bases are the same, so I can subtract. That's going to be x to the 3 take away a negative 5. So notice how, again, if I use the circle method, I have this 3, and I have this opposite of a negative 5. So notice how that really means the same thing as x to the third plus 5. So really it's the same thing as x to the eighth. Now, alternative way of doing it is if I have x to the third divided by x to the negative 5, at the very beginning, notice how there's this x to the negative 5 on the bottom. You actually could move it to the top. And when you move it to the top, it's no longer negative. This becomes this x to the third to the x to the fifth over 1, but we really don't need that 1 on the bottom. So it's really just x to the third times x to the fifth, which in turn just becomes then x to the eighth. And that would be another way to see the problem. So the 12x to the seventh or 8x to the fifth, notice how if you're not really good with fraction math, you could use prime factorizations. You could factor the 12 and you could factor the 8. I can use big T as an organizer. So remember, the prime numbers are like 2, 3, 5, 7, 11, sometimes 13. So notice how 2 does go into 12 6 times. 2 does go into 6 3 times. And 3 does go into 3 1 time. So I could change the numerator to 2 times 3 times x to the seventh. And on the bottom, notice how 2 does go in 8 4 times. 2 does go into 4 twice. And 2 does go into 2 1 time. So I could have that 8 changed to 2 times 2 times 2 times x to the fifth. So notice how I do have some factors that I can cancel out. I can cancel out some 2's there. So now we have this 3, and then there's this 2 on the bottom. And 7 minus 5 would give me 2, which gives me 2 on the top. That's going to be x squared. So 3x squared over 2 would be a way to write that answer. Now, again, you could have just saw the greatest common divisor. If you saw that you can divide the 12 and the 8 both by 4, that'd be an easier way to do it if you can see the common divisor of 12 and 8. So as we're talking about, manipulating negative and positive exponents, as I was mentioning, x to the fifth divided by x to the eighth, we can also write this as x to the fifth divided by x to the eighth. And remember, division is the same thing as multiplying by the reciprocal. such it still means x to the fifth times 1 over x to the eighth. And notice this is really the same thing as x to the negative eighth. So I can actually change this to x to the fifth times x to the negative eighth if you want to keep it as an addition problem. And that would be x to the 5 plus negative 8, which would give you then this x to the negative third. So that's what they're kind of doing here. So you can subtract 5 minus 8, or you can manipulate it where it's 5 plus negative 8. So notice that if you have a negative exponent at the very beginning, you can move it to the bottom like that. Or if it's in the bottom, if I have 1 over x to the negative third, notice how I can move this as x to the third over 1. But remember, x to the third over 1 is just the same thing as x. Now, one thing you cannot do is, if it's factors, if things are connected by multiplication and division, that's one thing. But notice how we have this x to the negative second plus this 1. This actually is two different terms. So this and this are two separate things. So we can't just divide. We cannot just move this x to the negative 2 down to the bottom and write this as 1 over 3x squared. This would not be a legal move. This would be a bad thing. Now, if you wanted to do it, you could separate it as, notice how they did this problem right here. You can separate it as x to the negative 2 plus 1 over 3 as two separate fractions. So you can break it apart as two separate fractions. And then you could simplify each fraction. So this would be okay here. This would be okay. But that doesn't look any better than what we started with necessarily. So we'll see what happens with our homework, but I don't think we deal with that a whole lot in our homework. So let's look at some of these examples here and see if we can simplify these expressions and make sure the answers have just positive exponents in them. So again, what I can do, again, there's probably more than one way to do this, as we're kind of pointing out here. But a lot of times what I like to do is I like to go ahead and get rid of the negative exponents. So now the speed of the negative third, it would go to the bottom, and the speed of the negative 1 would go to the top. So if I keep my mind straight, that a squared is going to stay put. That b to the negative 1's go to the top. That a on the bottom stays put, but that b to the negative third goes down next there with it. And so notice how there's two a's on top and one a on the bottom. I can cancel out one a, and I'm left with an a on the top. There's one b on the top and three b's on the bottom. So I can cancel out one b, and I'm left with two b's on the bottom. So that'd be a over b squared would be what we would consider simplifying. Okay, so simplifying kind of means to reduce when it comes to fractions, but also they want you to apply. We do not want the exponents to be negative either. So if I have x to the y to the negative 1 divided by xy squared, notice how I can move that y to the negative 1 to the bottom. So the x remains, but everything else stays on the bottom. The x on the bottom stays, that y squared stays, but that y to the first comes down there next to it. So what I can do, though, is simplify a little bit. The x's will divide out. So I don't have anything left in the numerator, so I have to put a 1 there, and y squared times y would be y cubed. So 1 over y cubed would be that answer. Notice on this one, we can't really do any canceling unless we separate it. So x cubed over xy plus y squared over xy. That would be the only way to deal with this problem, is to break it back into two separate fractions. Usually we're adding like fractions together, not breaking back apart. But if we did, we would have x squared over y plus y over x. But again, I would consider this an unnecessary step. I would just probably leave it as is. So the other thing we got going on is working with powers of powers. So an exponent raised to an exponent. So one things we can do in looking at this, if I have 3 squared cubed, we could rewrite this. This power 3 means there's 3 squareds. That means 3 squared times 3 squared times 3 squared. And since we have the same basis, I could say 3 to the power of 2 plus 2 plus 2. Well, that really just means 3 to the 3 2's. In other words, that's 3 to the 6. So what we pick up on is if there's a power to a power, what we can do is actually just multiply those exponents together and get 3 to the 6. So if I want to do x to the third to the fourth power, instead of changing it back to the multiplication rule, we can use what's now called a power rule. A power to a power, we actually can multiply those exponents. Write that as x to the 12th. So if I have 2 to the power of 2, I can write that as a to the 4th. N to the third raised to the 5th power, I can write that as n to the 15th. So if we can pick up on that, that gives us a way to kind of simplify it. So that's what this is saying right here is we could be applying this power here to do those problems. So another thing we can do is if you have a fraction raised to an exponent, that exponent can be brought through the numerator and the denominator. Just raise the numerator and denominator to that same power. So if I have 2/3 squared, one way to do this problem is actually just bring the exponent through and call this 2 squared over 3 squared. And therefore the answer would be 4/9. If I have -3 squared, the catch is with negatives, you have to put the negative in parentheses. So -3 squared over 4 squared. So a -3 times -3 is going to be a +9, and that's going to be a 16. Notice how again we have a negative number raised to an exponent. We want to put that negative number in a parentheses. So -1 cubed over 3 cubed. Well, -1 times -1 times -1 would actually be just 1 times 1 times 1 is 1, and 3 negatives still makes it negative. It just kind of goes back and forth like a light switch. So it's going to be, that's actually 3 cubed. So 3 times 3 times 3. 3 times 3 is 9, times 3 more is actually 27. So -1 over 27 would be that answer. Here, I kind of like it because its variables are a little bit easier. So this is going to be x cubed. And then I'm going to have on the bottom this y cubed cubed. So again, it's a good idea to show those parentheses there to kind of show a power to a power. So that's going to be x cubed over y to the 9th. And then here we would have x squared raised to the 4th power. And then we'd have this y to the 3rd raised to the 4th power. So we'd have x to the 8th over y to the 12th. So that's what we mean by kind of working out those examples with indicated exponents. Similarly, we can do this with a product inside the parentheses. If we have a product inside the parentheses, we're allowed to bring this outside exponent to the inside exponents. So it's kind of like the power rule again, a power to a power. So if I have ab squared, notice that the inside exponents actually were 1s. So 2 times 1 is actually 2. 2 times 1 there gives me a b squared as well. So that's how, again, that b's are actually raised to a power of 1. So again, I'm actually using the power rule, power to a power, and multiplying exponents. 3 times 2 would be a to the 6. 3 times 1 would be 3, and I have b cubed. So again, the power of 1 there for the x, that would give me x squared, and that would be a y to the 4th. That would be applying the actual rule to the problem. So 3x squared, again, if you want to apply the rule, this would be a 1, and this would be a 1. So it actually means 3 squared times x squared. But we actually have to simplify that coefficient and write that as 9x squared. So again, notice how that 2 has a power of 1 actually. So it's actually 2 to the 3rd power times x squared to the 3rd power times then this y to the 3rd power. So you actually have 8x to the 6y cubed. So again, if you can do it mentally, -5 squared means -5 times -5, that's 25. And then x squared, y squared. So sometimes it's easier to do it mentally and just write down the answer because sometimes it's hard to express your thinking on paper. Some things to pick up on as we move forward is the power rule only works if the inside is connected by multiplication. A plus b cubed, we cannot write that as a cubed plus b cubed. So this power 3 cannot come through there if we have addition present. It's got to be multiplication. Notice how the bases are not the same, so we cannot do anything with this. We cannot add those exponents together and write something else. Also, 3x squared and the quantity 3x squared. Notice how this 3x is in parentheses. These do not mean the same thing. This actually represents 9x squared. So these are not equal. So some things to pick up on. And similarly, if the coefficient's a negative, that actually means the opposite of x cubed. This really means 1x, I'm sorry, 1 negative and 3 x's. So don't get that confused. If I had negative x cubed, that would be 3 negative x's. And that would still end up being actually though negative x cubed though. Now, just same thing if I have negative 4 squared. Negative 4 squared actually means the opposite of 4 times 4. That's actually negative 16. If you want negative 4 squared, you actually have to use parentheses to make that happen. So negative 4 times negative 4, that would give us the 16. So watch out when math is written in this format. That does not mean negative 4 squared. It means the opposite of 4 squared. So that means there's only one negative present and two 4s. So the power only goes with the 4, not the negative. This negative is like a negative 1 coefficient. So it almost really means negative 1 times 4 squared is kind of almost what it means there. So keep that in mind.